Thank you. I'll speak about tropical currents. This is an ongoing joint work with Farhad Babaee. We haven't posted our paper yet, but if you become interested and if you want to know more details about it, I would be very happy to tell you more about after the talk. So let's start by setting up the stage. So if X is a manifold, then and K is a non-negative integer, we can think of this vector space that I'll write by d upper K, X, a huge vector space consisting of all smooth K forms on X with compact support. And we can equip this huge vector space with a suitable topology. The topology when you use in order to construct distributions out of smooth functions. And from that topology, you can define the dual of it that we write by d prime k, which is again a vector space, which consists of all continuous linear functionals defined on this vector space. So this is a set of all k-dimensional currents on X, which is by definition a continuous linear functional on the first vector space. This latter vector space is also equipped with a topology, the topology which says that every linear functional on d prime k, which is given by a point in the first vector space, is continuous. It's called the weak topology. And whenever I talk about limits of sequences of currents, then I'm referring to that weak topology. If X is a complex manifold, then I can write the first vector space as a sum of PQ parts that I'll write by dPQ of X. And correspondingly, I can write the second vector space as a sum of d prime of lower PQX, the space of PQ dimensional currents on X. And I'll talk about certain positive currents. So I'll say that an element phi in dPP, the PP smooth form on X, is positive if phi restricted to a subspace S is a non-negative volume form for all p-dimensional subspace S of the tangent space of X at X for all X. And dually, I'll say that a current, a PP dimensional current, is positive. An element T in the d prime of PPX is positive if it pairs with every positive form C non-negatively for all positive C in D of PPX. Yes. So the first notion is sometimes called weakly positive, and dually the second notion is sometimes called strongly positive. But this will be the only notion of positivity in this talk, so I'll just refer to them as positive forms and positive currents. So the most obvious example of positive current would be given by a p-dimensional complex subvariety So if V is a p-dimensional complex subvariety of X, then it defines a positive current, in fact, a pp-dimensional positive current that I'll write by bracket of V. So this lives in d prime of ppx, which is by definition a linear functional which integrates a given pp form over the complex manifold V. So in this talk, this bracket means a current rather than a cycle class. I hope that's not too confusing. So let's consider the case when X is a smooth projective variety over the complex numbers of dimension n. And then you can define a homology class out of closed currents. So by closed current, I mean this. You have an operator D defined on this space. And by taking adjoint, you have the operator D defined on the space of currents. And I'll say that the current is closed when D of that current is 0. And that defines a subspace of pp-dimensional currents consisting of closed currents. And there's a continuous map from this space to the h of n minus p, n minus p of x, mapping a current, closed current, to its cohomology class. So as with differential forms, current defines a sheaf, and this sheaf can be used to resolve constant sheaf and also sheaf of holomorphic p forms, and that defines a cohomology class out of a closed current. And this map is continuous with respect to the weak topology mentioned before. With the help of this map, we can define a closed subspace, d prime pp, subscript Hodge, which is the set of all pp-dimensional real closed currents such that the class of T lies in this Hodge of n minus p over the real numbers of X. So it's still a huge space. Yes, real. Yeah. And you can ask interesting questions about this space. So let's consider following 3 conditions. First is the familiar condition that Hodge of n minus p over q of x is generated by classes of p-dimensional algebraic cycles. This intersection of h n minus p and minus p with the, you take the intersection with the cohomology and look at the real vector space generated by those. And the second condition that I'll simply write as Hodge says that every current in this space, d prime pp x Hodge, is a limit of currents of the form lambda I of a vi where the sum is over I, and lambda I are rational numbers. So this bracket vi are currents defined by algebraic subvarieties in this form. And the third condition that I'll write by Hodge plus says that if I have a positive current, pp dimensional current, which lives in this space, d prime of Hodge, is a limit of currents of the form sum over I of a lambda I over vi, where this time lambda I belongs to non-negative rational numbers. This?
Yeah, could you just write it down? That way we just
Okay, let's do it this way. So, real vector space generated by h n minus p x cap h of a x of a c 2n minus 2p. And there are some known relations between these three conditions. And there are questions about them. Proved and posed by Mai. And his first theorem says that the first condition is equivalent to the second condition. And the hard part is to go from this to that.
It holds for the same set of x.
Yes, yes. For same x, same n, same p. Yeah. And the second statement of him is that Hodge plus, every positive currents with a suitable property can be approximated by this algebraic currents implies divergent without positivity. And you also prove that, quite interestingly, Hodge plus holds when p equals n minus 1. And the questions are whether Hodge implies Hodge plus, and very optimistically whether Hodge plus always holds. So one thing you can see from the tropical currents, or the construction of tropical currents, is the following. And there is a two-dimensional positive closed current T on a smooth projective variety X of complex dimension 4, such that 1, the class of T lives in H22X intersected with H4 X of a Z, and 2, the current T is not a limit of currents of the form sum over I of lambda I vi with lambda I positive, non-negative real numbers, where vi are irreducible surfaces contained in X. So by construction, you will see that it's clear that the Hodge conjecture holds for X. So Hodge holds, the first two conditions hold, but the third condition fails. So this converse fails, and this also fails. So that would be one motivation why you would like to know about tropical currents. But aside of that, I think in general it's rather interesting construction. So I'll speak about limit of currents, or more precisely, limit of currents of the form this. So let's see from some simple examples how such currents might look like. So the first example would be given by a limit of subvariety of this form that I'll write by Vm. So this is a subvariety defined by one equation, c to the m equals 1, a subvariety of C star. So it consists of m points. So you can easily visualize such thing. So this would be the case m equals 6. And let's imagine how the limit as m goes to infinity of 1 over m of the current associated to Vm would look like. So this Vm, that's the current defined by the subvariety Vm. That's a zero-dimensional variety. So zero-dimensional current, it should act on functions, and it basically evaluates the functions at these m points. So it's a collection of m Dirac delta measures, and you divide by 1 over m. So as m goes to 0, this Vm, subvariety Vm, tends to a dense subset of the unit circle S1 in a uniformly distributed way. So the limit of this current is clearly d of mu, or mu, where mu is the Haar measure on S1. So the limit current would be the current which says that if you give me a function, the value under that current would be simply the integral over the unit circle. There's a second example. By the way, there was nothing special about this polynomial. So if you start with any polynomial in one variable, fc equals 0, with the only one condition that constant term is non-zero, and if you look at the limit of the variety given by f to the zm equals 0, then you have a degree f many points, and as m tends to infinity, all the roots are accumulated into uniformly distributed dense subset of the unit circle. And the answer to the same limit question would be simply degree of f times the normalized Haar measure of S1. As a second example, let's consider the Fermat type curve, c1 to the m plus c2 to the m plus 1 equals 0. It's a curve, closed curve, inside c star to the 2. And let's imagine what limit as m goes to infinity of 1 over m of this limit integration current Vm would look like. So it's not so easy as before, but I believe that it's basically because of lack of ability to visualize c star to the 2. So if you could really see this, then I think the answer would be exactly as evident as in the previous case. But since we cannot really see these inclusions, so let's cheat a little bit and exploit the fact that this is really a hypersurface inside that. although our main goal would be to understand higher codimensional classes. So we can cheat using that fact and write this as a limit as m goes to infinity, 1 over m of I over pi partial bar and log of absolute value z1m plus z2m plus 1. So I'm using potential, but the point is, heuristically, it's easy to understand what the limit of potential would be. So almost everywhere. So there are basically 3 cases. So there are parts of C star to the 2 where the modulus of z1 is greatest among the modulus of z1, modulus of z2, and 1. And there are other parts where modulus of z2 is the greatest. And there are third part where the 1 is greatest among the modulus of the 3 numbers. So this should be I over pi of the function which takes the maximum of, I'm dividing out by m and canceling out this vector, of log of a z1 and log of a z2 and log of 1, and that's 0. And there are no limits anymore in this side, and we can try to understand what that would look like. So in short, this is I over pi of a derivative of certain piecewise linear function composed with log. And I'll write this current, limit current, as t of a c. So let's try to visualize how that looked like. Okay. So I have here 2-dimensional torus, C star to the 2. And I have this map mapping to the L2 that I wrote log. This is simply log of absolute value of Z1, log of a absolute value of Z2. And there's this piecewise linear function that I'll write by PL. That's simply max of a x1 and x2 and 0 mapping to all. So here x1 and x2 are real coordinates here. z1 and z2 are complex coordinates here. So the picture of this piecewise linear function here, that we can visualize, and it looks like this. So this is the origin of L2. And there are 3 parts in the plane. And the first part is where the linear function x2 is the maximum among the 3. And the second part is where x1 is maximum among the 3. And the third part is where 0 is maximum among the 3. And this defines a certain polyhedral complex that I write by C. So this C is the subscript C there. And this is a polyhedral complex that has 4 members, sigma 1, sigma 2, sigma 3, and 0, where sigma 1 is the first ray, and sigma 2 is the second ray, and the sigma 3 is the third ray, and 0 is the origin. And whatever the limit current Tc would be, it would be a current that is supported in the inverse image of this polyhedral complex C. Because otherwise, in all other parts, these derivatives are trivial. And we can also visualize this. So if you look at the inverse image of 0, that we know that it's a product of unit circles. And what's the inverse image of sigma 1? That's a family of real torides degenerating to this product of unit circles. So as you go from here to there, you're increasing the diameter of each one of the circles while keeping the two diameters same, or radius same. And in a similar way, inverse image of sigma 3 is also a family of two-dimensional tori, and this time radius is of one factor is going to 0, and this time radius of the other factor is going to 0. But now you notice something is simpler than before, because I can understand the current by locally looking at each point. So if I understand the current locally everywhere, then I know what the current is. And the current, if I restrict my attention to an open subset U1, and similarly U2 and U3, and you look at the inverse image, log inverse of a U1, then on this open subset, I have some understanding what the limit current look like. So if I look at this limit current and restricted my attention to this particular open set log inverse of U1, then that's, of course, I of a pi of a derivative of this piecewise linear function composed with log restricted to log inverse U1. But now there's something new. Now I can replace this piecewise linear function PL by another piecewise linear function PL1, where PL1 is simply the max of x1 and x2. And I don't have 0 here, because locally around all those points, PL is PL1. But now we can work the other way. We can invoke the same argument that was used in the first part of the example to conclude that this current here is a limit as m goes to infinity of 1 over m of algebraic current now associated to simpler algebraic curve, which is given by z1 to the m and z2 to the m equals 0. Because I no longer have this third term there. But now I'm restricting my attention to log inverse U1, which means that I'm looking at the complex manifold, which is not closed, but which is given by this equation and the condition that the modulus are same and both greater than 1. Well, this is simpler because I have one less term, and hence I have the factorization. So this is limit as m goes to infinity, 1 over m, and the sum of 1 to the m of the set z1 over z2 is e to the I zeta j, where z1 is greater than j, because this thing is a product of m linear forms, and each one of them gives you this equation, and you sum it over all those m irreducible components. And the same thing happens as before. So here e to the I zeta j are the m's root of unity, or m's root of minus 1. And as m goes to infinity, these roots of unity tends to a dense subset, uniformly distributed dense subset of S1. And you know that this is integral over S1 of d theta and d mu of theta. So here, d star is the punctured unit disk, or rather, I'm looking at the part where the modulus is larger than 1, so inverted punctured unit disk. So it's a complex manifold, and it gives a current, and you integrate those currents over as theta ranges over S1. And the point is that this whole thing depends only on sigma 1. And you can do the same thing over all other cells, sigma 2 and sigma 3, and get the equation Tc is T sigma 1 plus T sigma 2 plus sigma 3. One thing which is clear from the construction, but which is not that clear from the geometric description given here, is that some of these three currents are closed. Individual summands are not closed. So what I'm really doing here is looking at this total space of two-dimensional real torus in some other way. I can also look at it as the total space for the family of punctured unit disks, or the inverted such things. And each one of them have a boundary. And all of them have boundary at the inverse image of the origin, the two-dimensional real tori here. So if I look at the inverse image of 0, that's the torus. And if I represent it like that, and then the boundary coming from the first summand, T sigma 1, would be a circle, S1, which lies like this. If you pick one member of this punctured unit disk, and the boundary of that member would look like that. And if you also pick a one punctured unit disk which belongs to T sigma 2, then the boundary of that would look like this. And if you pick a one member of punctured disk from sigma 3, and the boundary would look like that. And certainly, these three does not cancel each other. But if you take the average over all members of the family, so that you have boundaries going in that direction, boundaries going in that direction, and boundaries going in that direction, well, then for mysterious reason, we know that they all cancel each other and gives a closed current.
This integral can one think to it as some three-dimensional object with a one form on it, and then that on the boundary one first use the restriction of this one form, and sum of three one form is 0?
I don't think I understand the question. Oh, but maybe we can talk later. So I can more somehow, maybe elegantly, express what this current is. So what I'm really doing here is to look at this log inverse of the interior of sigma 1 naught. So this sigma 1 naught is the real manifold. If I take the inverse image, so of the proper submersion, I have a 3 manifold here. And I've told you that this can be viewed as a family over sigma 1 naught of two-dimensional real torus. But you can also view it as a family over S1, where this map pi 1 or pi sigma 1 is given by the argument of Z1 over Z2. And the virtue of the second map is that all its fibers are complex manifolds, the punctured unit disks. And whenever you have such a map, so oriented submersion, and if I have a measure, the Haar measure d mu on S1, which I can view as a zero-dimensional current, I can pull back the current, zero-dimensional current, into a one-dimensional current here. So pi 1 pull back over d mu And that's what I mean by T sigma 1. Or more precisely, I can extend by zeros of this current on here to the entire C star 2. And that's what I mean by T sigma 1. Can I use the slides? Okay. So I hope you got a sense of what tropical currents would be. So so I'll very quickly go over what the tropical currents are. So this would be a somewhat less interesting part of the talk, which consists of definitions and theorems. But the main point is that what you saw from this example holds in general, and not just for hypersurfaces, and can be done for arbitrary codimensions. So all you need is logarithm map and the argument map defined on C star to the all and S1. So you can view it as simply this manipulation of polar coordinates. So if you have a finitely generated abelian group, and then there is a logarithm map and argument map for that n, coming from the complex torus associated to n, C star times n, and the compact real torus S1 tensored with n, and the real vector space all tensored with n. And this behaves as expected. So if you have a rational subspace of Ln, by that I mean a subspace generated by integral vectors, then you can form this argument map and logarithm map for this original z to the n and h intersected with z to the n and their quotient spaces. So here you see complex torus, here you see real compact torus, here real vector spaces, and the logarithm map and argument map commutes with the canonical maps. And this is the map pi, the second submersion that realizes the log inverse of a rational space H as a total space of the family of complex manifolds, as defining by composing it with argument map, mapping to S1 to the n, and to the real torus of the quotient space. So this would play the parameter space S1 you have seen before. And this is, in fact, a homomorphism of Lie groups. And you can easily see that the kernel of this homomorphism is exactly the complex torus associated to H. And all other fibers are translations of the kernel. And you can do the same thing for not just for rational subspaces, but for affine subspaces, because all the affine subspaces are translations of rational subspaces. And you pick any point from the affine space you have chosen, and you basically define the same map pi a by translating with respect to the chosen element by taking the exponential. And the map doesn't depend on the choice of a. And if you have a rational polyhedron, then you have the affine span of a rational polyhedron, and you have the interior of rational polyhedron, and it defines a linear subspace parallel to the affine span. And it defines, as in the theory of toric varieties, it defines a certain lattice that I'll call a normal lattice, which is defined as a quotient of z to the n by the lattice of h sigma, which is the linear subspace parallel to the affine span. So there are corresponding real vector space and a complex vector space. And this sigma defines the projection pi sigma that we have saw before. So the domain of such map is the inverse image of the relative interior of sigma. So that's a manifold. And it maps to the real compact torus associated to the normal lattice of sigma, simply by obtaining this restricting the map pi associated to the affine span of sigma. And each fiber, pi sigma inverse, is a p-dimensional complex submanifold of C star to the n. And the point is that this submanifold, this complex manifold, has a boundary. But if you start with a polyhedral complex that meets each other in the right way, and if you take the average of such boundaries at the boundary of such cell complexes, then they will cancel each other. So you define a certain complex pp dimensional current T sigma of mu associated to any complex Borel measure on the real compact torus associated to the normal lattice of sigma by integrating along the fiber. So each fiber is a complex manifold. That's a pp dimensional current. I can take the average of it with respect to any complex Borel measure. Yeah, the value of the measure is a complex number. So if mu is a positive measure, or just measure in the usual sense, then this will be a positive pp dimensional current. And that's if and only if. So in the particular case when we are dealing with the Haar measure normalized by the condition that the integral is 1, then I'll write it without mu. But it will be helpful, you will see, to develop this in more general setting. And this is the complex C you have seen before. So I'll say that a polyhedral complex is a p-dimensional weighted complex in all n if each maximal cell sigma in the polyhedral complex is rational, meaning that it's defined by a set of rational inequalities, and it is pure dimensional. Every maximal cell is p-dimensional. And I'm going to assign a complex number W to each p-dimensional cell. So it's basically a pure dimensional polyhedral complex assigned with a complex number to each maximal cell. And I'll say that that complex is positive if all the weights are positive or non-negative. And I can also define the support of such weighted complex as the union of cells with non-zero weight. And whenever I have such weighted complex, I can define a pp dimensional current Tc. So this is the Tc you have seen before. So it's defined over sum over all the maximal cells multiplied by the weight I have assigned. This is a complex number. And the current that I've constructed before, T sigma, associated to any rational polyhedron. So it's basically the pullback of the normalized Haar measure on the real compact torus associated to sigma along the submersion, oriented submersion pi we have constructed before. So there are no strange measures involved here. So all the measures involved are normalized Haar measures on S1 to the S1 times n. And so so this would be a tropical current, and why am I calling this tropical? Because these currents, currently associated to any polyhedral weighted complexes, behaves in a very nice way if the polyhedral complex is a tropical variety. So let me tell you what tropical varieties are. So whenever I have a codimension 1 phase of a maximal cell, sigma, then the difference of sigma and tau, so this is p-dimensional and that's codimension 1, that generates a ray in the quotient space defined by the subspace of tau. And I'll write u sigma tau for the primitive generator of that ray. So I have associated to each pair of a p-dimensional cell and its codimension 1 phase, I have this integral vector in the quotient space. And this weighted complex satisfies the balancing condition at that codimension 1 phase tau if the sum of all the weights times that primitive vector is 0 in the normal space of tau, where tau is the codimension 1 phase. So it's a certain condition. It's a bunch of linear conditions involving the possible weights on the weighted complex. And weighted complex is balanced if it satisfies this balancing condition at all codimension 1 cells. And tropical variety is a positive and balanced weighted complex And tropical current is the current you have seen before, associated to a tropical variety. And the fact we have seen before generalizes in this setting. And one of them says that a weighted complex C is balanced if and only if the associated current is close. So the valuable direction would be that. So if I start with a tropical variety, and if I construct this current here, then I would get a positive closed current. The examples obtained in this way can be manipulated to have many interesting behaviors if you select the right tropical variety. And one of them is this. So you say that the normal closed current T is strongly extremal if for any other normal closed current T prime, which has the same dimension and support, there is a complex number C such that T prime is C times T. So normal here means that the current has measure coefficient, not crazy distribution coefficient. And this is a very strong condition. It's a condition on the support of the current T. And it says that on that support, there is essentially one current up to constant multiple, which has that as a support, given dimension. And one example of a strongly extremal current, you already have seen one example, the current associated to p-dimensional algebraic subvarieties. So if you give me any pp-dimensional current whose support is exactly a p-dimensional irreducible subvariety, I know that that current is some multiple of that integration current. But there are other examples, and you will see shortly. So if you have a positive and strongly extremal current, then in fact that generates the extremal ray in the cone of positive closed current. That's a huge cone. And here is the definition you would expect. And I'll say that the balanced complex C is strongly extremal if for any balanced complex C prime, which has the same dimension and support, there is a complex number C such that C prime is multiple of C. So this is a linear algebraic condition. If I have a complicated polyhedral complex associated to each codimension one phase, I have this balancing condition, a linear equality. And you can solve that linear equations locally everywhere at each one of its codimension one phases. And the condition here is that the space of solution is one-dimensional. There's only one weight that could balance the given polyhedral complex. And the second theorem would be if you have a non-degenerate weighted complex, meaning that it's not contained in proper affine subspace of Rn, then that is strongly extremal if and only if this tropical current is strongly extremal. So again, the valuable direction would be this. So there are many combinatorial tricks to come up with, or linear algebraic tricks to come up with a strongly extremal weighted complex. And then associated to that, I have a strongly extremal current. And if all the weights are positive, I have a positive current. So there is a systematic way of obtaining strongly positive closed pp-dimensional currents. So I'm running out of time. So all of this proof involves a little bit of Fourier analysis on this real compact torus, and everything works quite nicely. Okay, so the point is that, okay, so let's stop with theorems and close with one last example of tropical currents. How can I lift this? So let me just give you some flavor of this computations. So when I have a two-dimensional weighted fan, say in L4, then I can view it as a graph on a sphere, S3. Since I don't have enough time, let me content myself with one smaller dimensional example. Which consists of this. So this is a graph, a geometric graph with vertices plus minus 1, and plus minus 1. And to each vertex, I'm imagining a ray obtained by connecting it to the origin. And to each edge, I'm really thinking of a two-dimensional cone, the cone over that edge. So this is a two-dimensional polyhedral complex which entirely consists of cones, two-dimensional cones and one-dimensional cones in all three. And I want to balance this. So I want to assign edge weights to each one of these edges so that everything is balanced. So if I start with assigning edge weight 1 here and consider the balancing condition at this point, it amounts to solving the linear equation 1, 1, 1 is a sum of its neighbors, and there are 3 of them. And my goal is to fill in the blanks so that the equality holds. But this is a corank 1 linear system. So if I start by assigning 1 here, then there are no other choices. The only solution with 1 filled in here would be 1, 1, and 1. So I should have 1 here and should have 1 here. But I can do the same reasoning here. Now if I take the balancing condition here, the only possible solution would be 1 here and 1 here. And the solution propagates, and for some dramatic reason, it meets up. And this constant weight is the only possible balanced weight this polyhedral complex can have. So if you construct the tropical current out of this combinatorial linear algebraic object, then you will automatically have a strongly extremal current. Although this is a two-dimensional fan in three-dimensional examples, you could cook up a whole lot of other examples starting in dimension 4 and come up with a strongly positive closed current of two dimensions. And the point of this construction is that if you have a strongly extremal current in that way, and if you know that if it's a limit of algebraic currents, then it should be also a limit of currents associated to irreducible varieties. This is some sort of convex analysis developed in the infinite dimensional setting. But there are many other restrictions of a current being not just a linear combination of algebraic currents, but a single irreducible currents. And there are other interesting combinatorics you could develop starting from here, related to tropical Laplacians, et cetera, to deduce the statement I have claimed before. So I'll stop here. Thank you for your attention.
Silly question, but I'll ask. So this gives an example in dimension 3 or something. So I guess could you try to say more about how the example in dimension 4 works or how it's different?
So that's an example that I could not do because of the lack of the time. So this example that could not be approximated by the algebraic currents comes from this picture. So you start with this graph, K44. And there is a good reason why you would start from K44. And I want to realize this combinatorics by a two-dimensional polyhedral complex in R4. So as before, these vertices are actual points. So let's say this is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And you put these points in appropriate positions. And try to make the balancing condition work. Before doing any computation, you know that this is strongly extremal. And the reasoning is the same. At each one of the vertices, the collection of all its neighbors are linearly independent. So locally, the balancing condition admits a unique solution. So, and that propagates through the whole edges because the graph is connected. So if there is a solution, there is at most one up to a multiple. I know that beforehand. The balancing condition at the right-hand side are easy. So it simply tells me that I should assign edge weight x1 here, and edge weight y1 here, edge weight z1 here, edge weight w1 here, and same for the other vertices. And the interesting condition comes from the balancing condition at the left-hand sides. If you think about it, the condition is quite neat. It says that the whole weighted complex is balanced exactly when the matrix 4x4 matrix you see in this side is an orthogonal matrix. Right? The balancing condition here means that x1 times that, x2 times that, x3 times that, x4 times that should add up to some multiple of 1, 0, 0, 0. And that gives you the orthogonality. So, and if you pick a sufficiently general orthogonal matrix with integral entries, and you can do that, and fill up here. I prepared here one example, but maybe. Then what you notice is the following. Any orthogonal matrix should necessarily involve negative entries. So I have one example where it has only 3 negative entries, but it's not very important. The point is that if this is a strongly extremal current, and if you look at the support, then it would give a certain stratified space which does not support any positive current. But now, if you have a negative edge, say one is here, then exploiting the fact that you live in the 4-dimensional space, you can go around. So this is a positive cone with, say, negative weight 1. Then what you can do is I can delete this cone and replace with 3 other cones here, now with positive cones. And this does not screw the balancing condition, because I have taken the negative of the vectors and negative of the weights. But somehow this violation of convexity gives you what you want. So each time you apply this going around construction, and they do not screw up each other because you live in the 4-dimensional space. And then each time you apply this balancing, this going around construction, you're introducing one more negative eigenvalue to the what I call tropical Laplacian, which I haven't introduced. But the point is that if something is approximable by irreducible outright varieties, then its tropical Laplacian should have exactly 1 negative eigenvalue. So this would give an extremal tropical variety which has many negative eigenvalues in its tropical Laplacian and cannot be approximated by such thing. Yes. So this, the current T that I have stated in the very first statement, if I take the cohomology class, then this is effective. So the cohomology class itself is a linear combination of cohomology classes of subvarieties. And it has other interesting properties. It's It's also NAF, but not just NAF. Because of this extremality, it spans an extremal ray of the NAF cone, if you care about the NAF cones for the higher codimensional cycles. And yeah, this is one thing you can play with tropical currents. So I hope I managed time better, but I'll stop here.